Okay, so this time we're going to take a look at a harder problem. In this case, I'm going to introduce something that we haven't really dealt with before, but it's something that we should get used to because they're the sort of thing that show up a lot in regular life. We're going to introduce a pulley this time, and it's going to make things a little bit weird. Now, I mentioned pulleys briefly in class, and I talked about how I describe them as basically bending the coordinate axis around it. Okay? And we're going to see how that works out here. Pardon me. So I've got a pulley, and I'm going to assume that it's frictionless. Usually we will, because we just want to get the effects of the pulley without having to pay too close of attention to any of the real-world effects that it might bring in. Now, pretty good pulleys, they'll have very low friction, so it's an approximation, but it's a pretty good one. And what I'm going to do is I'm going to have two masses hanging from them. I've got 3 kilograms here, and that's tied over to the other side where I've got 6 kilograms. Okay, so I've got my drawing. In this case, my problem is going to be that I'm holding on to the 6 kilogram, or the 3 kilogram for that matter, and I'm supporting it so that they don't move. And then I let go, and I want to know what their acceleration is, how fast they're going to start moving when I let go, and I no longer introduce my normal force to help hold them up. Now, we've got a drawing, we've got an idea of what we're looking for, and the next thing that we do is we're going to label our coordinate axis. We'll do up as the plus y, but here's where the pulley makes things complicated. If my mass here, my 3 kilograms, goes up in the plus y direction, which direction does my 6 kilogram mass go? Well, because they're tied together, as this one goes up, this one has to go down. So, what qualifies for this guy as a movement in the positive y direction, I've got to describe the same thing over here. So if this guy moves up a little bit, or I'm sorry, moves in the positive y direction a little bit, this guy needs to move in the positive y direction as well. Which means, with this pulley, I end up bending my coordinate system around it, just like I told you before. Now this is going to seem weird, okay? That over here, for this guy, the positive y direction is actually going to be down. But I need to do that because the movement of one guy in the positive or negative direction has to be the movement of the other guy in the positive or negative direction. It's the same reason that we talked about with them being tied together, their accelerations are the same. We need to set up our system such that we keep track of them together. Okay, so for that to happen, what we need to do is when one of them moves in the positive direction, the other one also has to move in the positive direction, so we've got to set up our coordinate system to do that. And again, this is where pulleys can become confusing for people who are not used to them. Because basically what it's done is the coordinate axis bends around that pulley and then ends up pointing down over here. We'll see what we get, and I'll describe to you what happens if we don't keep track of that, if we don't do this, because we won't end up with the correct answer. Okay, but I've got my drawing, I've applied my coordinate axes pretty well, and so now I'm going to apply my free body diagrams, or draw my free body diagrams, so I can see what's going on force-wise. So free body diagrams, I've got 2 objects, like we did with the wagons, and so I'm going to draw 2 free body diagrams. So this one is going to be for our 3 kilogram, which we will call mass 1, and 6 kilogram, which we will call mass 2. This will be object number 1. Okay, well I've got, this is near the surface of the Earth, so I've got mg, my force of gravity. In this case it's mass 1 times gravity. And it is being held up by a tension that's in the positive y direction over here. Okay, well, no other forces here, so I'm going to take a look at object number 2. And object 2, in this case, my positive y direction is downward, but I've got gravity and 2g pulling down on it, right? And I've got that tension pulling it up. Now remember, with this being a wire or a rope, we discussed this in class when we talked about tension. Tension is kind of the same throughout the entire rope. Okay. So, what I'm going to do now is, now that I've got my forces where I can see them, I'm going to apply Newton's second law. And I'm going to do sum of forces in the y on object number 1. Okay? Well, for object number 1, up is the positive y direction, so I've got a positive t minus mg, where it's mass 1, and that's equal to mass 1 times the acceleration on the y. Okay? Sum of forces in the y on object 2. Now on object 2, remember our coordinate system for object 2 points downward for the positive direction. So in this case, I end up with mass 2 times gravity being positive, because down over here is my positive direction. And that seems really weird, but trust me, it's important. And then I'm going to do minus t, because my tension is actually pointed up against the coordinate system. And I'm going to set that equal to mass 2 times acceleration in the y. Okay, so I have my 2 Newton's second law. Pardon me. And so I've got a problem. So I know my masses, those are good. I know g, so masses and g. But both of these equations, they've got tension that I don't know, and they've got acceleration in the y, which luckily we know that the acceleration in the y for both of them is the same because they're tied together. That's one of the reasons why we've had to do kind of the weird thing with our coordinate axis. But we know that these 2 accelerations are the same. We know that the tensions are the same. We just don't know what they are. On the upside, we've got 2 equations, which means we can get relationships. So I'm going to take a look at this first equation here. T minus mass 1 times gravity equals mass 1 times acceleration in the y. I'm going to add mass 1 times g to both sides. And that gives me that my tension is equal to mass 1 times my acceleration in the y plus mass 1 times gravity. Okay, well now I have an expression for what t is. I can't solve it, but t equals this stuff. I can actually then take this and plug it back in up here. So, plugging the first equation that I've adjusted here into the second one, we end up with mass 2 times gravity minus, I'm going to plug in for my t, mass 1 times acceleration in the y plus mass 1 times gravity. So there's my t, my tension. I'm going to set that equal to mass 2 times acceleration in the y. And there's a train going by. Okay? That's pretty good. We're starting to make progress here. So I've got mass 2 times gravity minus mass 1 times acceleration in the y. Now remember, this minus is minus the whole thing, so that plus sign becomes a minus, distributing that. Mass 1 times gravity equals mass 2 times acceleration in the y. Okay, well I want to get acceleration in the y all on one side so I can solve for it. So I'm going to add mass 1 times acceleration in the y to both sides. Mass 1, acceleration in the y. And I'm going to get a result. I'm going to go ahead and put it up here. Since I've had to switch to my other camera, I think I've got more room here. Pardon me. So bringing that up here, I now have, let's see, mass 2 times gravity minus mass 1 times gravity equals mass 2 times acceleration in the y plus mass 1 times acceleration in the y. Well, I factor in acceleration in the y out of here, out of both of these terms, and I have mass 1 plus, or I'm sorry, mass 2 plus mass 1 times acceleration in the y. These are the same thing. I just pulled the acceleration in the y out of there to get it by itself. Equals, I can do the same thing over here. I'll have mass 2 minus mass 1 times g. We're almost done. I'm going to divide both sides by mass 2 plus mass 1. Mass 2 plus mass 1. Okay. And now I've got my acceleration in the y which is this guy here, equals mass 2 minus, minus mass 1 times g over mass 2 plus mass 1. I plug in my values, and that's going to be 6 minus 3 kilograms divided by 6 plus 3 kilograms times g. And so that'll be 3 divided by 9, which is going to be 1/3. AY equals 1/3 g. And I find, bringing it back over here where I have a little bit of room, AY equals, if I take 1/3 times gravitational acceleration, I end up with 3.27 meters per second squared. That's the acceleration that they will experience. Okay? So let's take a look at this logically and see if we can verify our answer, if it makes sense. So when I let go of these guys, gravity's pulling on both of them, right? So if the 3 kilogram mass weren't here, then this guy would just fall outright. But since gravity's pulling on both of them, it's kind of slowing it down. So we've got a term over here where we've got the difference between the two mass, the difference between the tug of war. So for instance, if you think about it, if this were 6 kilograms and this were 6 kilograms, well, they'd be perfectly balanced, right? If I put the same amount of weight on both sides, it wouldn't go anywhere. Okay? And that actually carries through in our equations, because if they were the same mass, this would go to 0 and our acceleration in the y would be 0. But they're not the same mass. And so it's kind of a tug of war. If you have the same amount of force on both sides, then they're going to sit there. If you have a little bit more over here, then it's going to slowly accelerate. If you have a whole lot more over here, then it's going to accelerate quickly. It's like having a bunch of people pulling on one side and only one person pulling on the other side. Not a good day for the person on the other side. So that's what this term is saying, this mass 2 minus mass 1. It's telling us the bigger distribution, or the bigger difference between those two masses, the bigger this number is going to get, right? This will be a much larger number, times g, and then we'll end up with a greater acceleration in the y. Now the biggest that we can get, obviously, is about g itself. But let's look at what it's divided by. So this tells us about our net force, basically how much is pulling on one side versus how much is pulling on the other side. Okay? And so, down beneath, up here, this is kind of telling us about our full force, our net force. How much is pulling on one side, canceling out how much is pulling on the other side, and whatever's left over. And so, by Newton's second law, well, that's kind of like what we have here. If we could imagine this, that's our sum of forces. It's how much one is knocking out the other. And we would set that equal to whatever the mass is times its acceleration. Well, we have the acceleration over here. The combined mass, the total amount of mass that gravity's got to get moving with that force, is all of this together, because it's got to accelerate both the 6 and the 3 kilograms. And so that's what we've got here. This is our combined mass. Alright? Now this is very close to what is normally called a reduced mass, but I think we'll see that in the next problem when we deal with an inclined plane. Now finally, if we did not keep track of this coordinate system, where we had plus y coming up here, and then bending it around the pulley and making plus y come down here, then the way that we've done the math, we would have ended up with mass 2 minus mass 1, and then this would be mass 2 minus mass 1, and we just get that the acceleration is equal to the gravitational acceleration, which doesn't make sense. Because in reality, gravity is trying to pull on both of these, and so gravity pulling on this guy is actually going to slow this guy down. And again, if you think about it, if both of these were the same mass, where I've got 6 kilograms here and 6 kilograms here, then they would just sit there. They wouldn't actually accelerate at all. Okay? So this is a more complicated problem, but we can still approach it using Newton's laws. The biggest thing that we've got to take care of, though, is we've got to remember that that pulley is there, and pulleys make weird things happen to our coordinate systems. Now, I won't do too much in class with pulleys, but I want you guys to see them and have an idea of how they're used. In full reality, they show up fairly often in life, mostly because they're very useful at redirecting forces. We had talked about that, and that's what they're doing. They're redirecting forces back around. Okay? Now, as a reminder of what we did, we drew our picture, we labeled our coordinate axes, which were very important for our pulley, and then we did our free body diagram. We drew out our forces to keep track of them. We applied our Newton's second law to get a series of equations, relationships, and then we went through and started doing math on those equations from Newton's second law to solve for what we want.